Source Coding, Chapter 2 of Information Theory, the art of turning messages into efficient, decipherable code. Here's the core problem. A source produces symbols, letters, numbers, sensor readings, and we need to send them through a channel. But the source and the channel speak different languages. Source coding is the translator. It adapts the source to the channel, and along the way, it compresses the data by removing redundancy. The goal is simple: transmit the same information using fewer bits without losing anything. Let's define the terms. A source S produces messages from a set of symbols. We encode each symbol using an alphabet. For digital communication, that's binary, zeros and ones. The result is a code word, and the collection of all code words is the code. The average code word length is the weighted sum of each code word's length, weighted by its probability. And here's the critical constraint. A code must be decipherable. You need to be able to look at a stream of bits and know exactly where one code word ends and the next begins. The simplest way to guarantee this is the prefix condition. No code word is the prefix of another. Codes that satisfy this are called instantaneous codes. A code is only useful if we can decode it. Decipherability means that when you receive a stream of bits, you can separate the code words correctly with no ambiguity. The simplest way to guarantee this is the prefix condition. No code word is the beginning or prefix of another code word. For example, if 01 is a code word, then 010 cannot be 1, because you wouldn't know if the stream 010 means 01 followed by 0, or the single word 010. Codes that satisfy the prefix condition are called instantaneous codes, because you can decode each word the moment its last bit arrives. No looking ahead needed. Now, how do we measure how good a code is? Efficiency is the ratio of the minimum possible average length to the actual average length. Redundancy is the complement, the wasted bits. But what is that minimum? Shannon's first theorem gives us the answer. For a source with entropy h of s, using an alphabet of size d, the average code word length L can never be less than h of s over log base 2 of d. And we can always get within 1 bit of that limit. This is the fundamental bound, the absolute lower limit on how compactly we can represent a source. So how do we actually build a good code? The Fano-Shannon algorithm is one approach. It works in 3 repetitive steps. First, sort the source messages in order of decreasing probability. Second, divide the list into 2 subgroups whose total probabilities are as close as possible. Assign a 0 to one group and a 1 to the other. Third, repeat this division on each subgroup until every message is isolated. The path of zeros and ones from the root to each message becomes its code word. This algorithm doesn't always produce the absolute optimal code, but it gets very close. It's what we call a quasi-optimal code. Let's see this in action with a concrete example. We have 8 messages with probabilities ranging from 0.4 down to 0.02. Fixed length coding would use 3 bits per message. Simple, but wasteful. The Fano-Shannon code, built by repeatedly splitting the probability list, gives an average length of just 2.59 bits per message. That saves 0.41 bits per message compared to fixed length coding. Over 100 messages, that's 41 bits saved. But the theoretical limit, the entropy of this source, is 2.48 bits per message. So the Fano-Shannon code is close to optimal, but not quite there. An optimal code would save 52 bits per 100 messages. To recap, source coding is about representing information efficiently while keeping it decipherable. The prefix condition guarantees we can decode on the fly. Shannon's first theorem sets the fundamental limit, the entropy bound. And algorithms like Fano-Shannon let us get close to that limit in practice. Every time you zip a file or stream a video, you're relying on these same principles. Source coding is the invisible engine that makes digital communication possible.